Hi, I'm Aidan from the Gwinnett County Public Library. Welcome to this last instalment in our series of Codemaking and Codebreaking. In this series, we've explored the fascinating world of codes and ciphers. We've explained how some of them came about and how you can solve them. In our previous episodes, we have looked at quite a few codes and ciphers which could be described as monoalphabetic substitution ciphers. Those are ciphers in which changes would be made to individual letters, and each letter would be replaced by the same letter or symbol. So the great thing about those ciphers was their simplicity, but that simplicity came at a cost. If you remember, monoalphabetic substitution ciphers are particularly susceptible to being solved using frequency analysis. Now today we're going to look at a different type of cipher that works in a different way. Rather than encrypting one letter at a time, we're actually going to encrypt letters as pairs. This type of cipher is described as a digraph or digram substitution cipher. Now a digram or digraph is a pair of successive letters, such as the SH in the word shoe. So the idea behind this is that you're going to be able to increase the number of substitutions possible. Instead of having 25 possible substitutions, you have at least 600. And a letter can be represented by many letters or symbols in different places in the same document. This should make frequency analysis harder to do. The first person that we know of to try and create this type of cipher was Jean-Baptiste de la Porta in the 16th century. His cipher substituted symbols for each digraph, but this proved impractical. It was too much to memorize, meaning that if someone wanted to use it, you had to keep a physical copy of the table near you at all times. From a security perspective, this is a terrible idea. The first real use of this type of code came centuries later, in 1854, with the invention of the Playfair cipher, which is sometimes referred to as the Playfair square. The inventor of the cipher was Charles Wheatstone. Now, Wheatstone was a prolific inventor. Among his many inventions were the English concertina, which was a musical instrument, the stereoscope, which was an early form of 3D viewing equipment. This actually allowed you to see a photograph in 3 dimensions. And he was also responsible for many of the developments around the electrical telegraph system that we discussed in our last episode. Now, Wheatstone's original purpose in inventing this cipher was to make it possible to encrypt confidential information for communication through the telegraph system. However, his friend, Lord Playfair, soon realized that it had other potential applications. Now, Playfair was a scientist himself, and he went on to become a member of the British government. And throughout the latter half of the 19th century, he advocated for its use in diplomatic and military scenarios. The Playfair cipher needs no special equipment. You can actually use it using a piece of paper and a pencil. The only thing you need to know is the keyword that was used when the message was originally encoded. This made it ideal for use in the field. You begin with a 5x5 square like this one, and you select your keyword. For our example, let's be creative. We'll use Playfair example. We begin to fill in the squares from left to right, top to bottom. Now, each letter can only appear once in the grid. Now, you may have noticed that we only have 25 slots, and of course there are 26 letters in the English alphabet. Most versions of this cipher treat I and J as the same letter. And the reason for this is it's easy to tell from the context of the letters around it which of those 2 letters is intended. We will fill in the remaining letters of our alphabet in the spaces that are left in our grid. Now, let's take our message and break it into digraphs, pairs of letters. We're going to do it like this. Now we can begin to work out the substitutions for our pairs of letters, and we do this using a small number of very simple rules. First, we look to see if there are any digraphs in which the same letter is used twice. In my example, you will note that there is a double E. We're going to replace the second E within the pair with the letter X. We do this because the letter X is uncommon, so we'll notice that it's incorrect when we come to decode it. If our message ended with a single letter, we would also add a letter X to the end to complete a digraph pair. There are 3 other rules. If the letters from a digraph appear on the same row of your table, replace them with the letters to their immediate right respectively. Now, if one of these is on the end, you're going to wrap around to the other side of the grid. If the letters appear on the same column of your table, replace them with the letters immediately below respectively. And once again, you'll wrap around if it's in the bottom row. Lastly, if the letters are not on the same row or column, replace them with the letters on the same row respectively, but at the other pair of corners of the rectangle defined by the original pair. The order is important. The first letter of the encrypted pair is the one that lies on the same row as the first letter of the plain text pair. Now look, I know this sounds really complicated, and the best way to demonstrate how to do this is to show you it in practice. The first digraph in our message is TH, which you will see here on the grid. The third of our rules will apply to this pair as they are not in the same row or column. So we imagine a rectangle with those 2 letters as corner points. And the letters that are at the other corners, which would be B and Z, will replace them. Now remember that the order is really important. The first letter of the original pair is T. So the first letter of the substitution will be Z. So our first pair will be ZB. The same rule applies to our second pairing, IS, which becomes MK. And to our third pairing, CO, which will become DN. Our next pair, DE, are in the same column. So here we need to use the second rule. We will shift downwards 1 space so that DE becomes OD. Our next pair, IS, we've actually done earlier, and so we can repeat that. It's going to be MK. Our next 2 letters are just the other way around, so we can reverse the order to get KM, because the S is the first in the pair this time. MP will become IF. LE becomes AR. RT is IU. HA is DF. NI is KR. And TS is ZK. Now we come to our double E, which is now represented as EX. These are in the same row, and so we will shift 1 space to the right. EX will now be XM. Our final pair, MS, are in the same column, and so they each move down 1 space to become HZ. So that's how you encode a message. How do you go about decoding it when you receive it? Well, the person who receives the message will need to know the code word, and they'll need to construct their own version of that same table, and it works exactly the same way. Go left to right, top to bottom, and no letter can repeat itself. To decode a digraph where both letters are in the same row, instead of moving to the right, you move a space to the left. XM thus becomes EX. To decode a digraph where the letters are in the same column, you're going to move up a space. OD shifts up 1 spot to become DE again. And the final rule works in exactly the same way it did before. Find your 2 letters that are not in the same row or column and make a rectangle with them. And then use the other 2 corners to find the other letters. Remembering, of course, that you start with the letter that's in the same row as the first letter in the digraph pair. So the second letter will be the other corner. In our example, ZB becomes TH. Let's quickly fill in the other letters to finish our decoded message. We need to remember that the letter X may have been used for duplicate letters within a digraph. If the second letter in a digraph doesn't seem to make sense, try replacing it with the first letter within that same pair. If there's a lone X at the end of your message, it's an extra that was put in there to make up a pair, and so you can disregard it. Okay, so hopefully you've got the basic idea. What we're going to do now is try decoding a message yourself. Now for this, we're going to use a different keyword. This is going to be codemaking and codebreaking. And what I want you to begin by doing is seeing if you can construct the table that you would need to use to decode your message. Now remember that I and J share a space. If you want to try it, press pause now. Okay, so what you should have should look like this. If it does, great job. Here is the coded message that you've received. Now, I've put the decoding rules on the screen as a reminder along with the grid. Why don't you see if you can solve it yourself? Remember to start by breaking your coded message into digraph pairs. Pause now if you want to give it a try yourself. Okay, so let's work together to try and solve this. YT are in the same column, so we have to move them up one space. They become TH. KG are in the same row, and so we move them one space to the left to get AN. NW are not in the same row or column, so they make a rectangle and they become KY. Same with MQ, which gives us OU. RD becomes FO. BQ is RP. BG is LA. XN is Y, and either I or J, and we'll have to look at the letters around it later to give us context to help us figure that out. GA are in the same row, and so they'll each move one space to the left. Remember that the letters will wrap around to the other side of the grid if there's no column to the left of a letter. So G becomes N, and A will move to the other edge of the grid to become G, NG. GB will be AL, EK becomes ON, AK are in the same row, and so we move them a space to the left to give us GA. YT are in the same column, so we're going to move up one space to give us TH. DC are in the same row, so moving them a space to the left will give us OM, and that leaves us with DY, which will become EX. Now let's take a look at our decoded message and try and work out the words they may represent. As you can see, there is an extra X at the end, which was needed to make an even pair. You should have got, "Thank you for playing along at home." So that's how to decipher it if you know the keyword. And as you can see, while it's a little more complicated to use than the monoalphabetic substitution ciphers, it is still relatively simple. You only need to use 3 or 4 rules in encoding or decoding, and the more you do this, the easier it will become, like any skill. The question is, how do you go about cracking this code if you did not receive the keyword? Earlier in the video, I mentioned that there are 600 possible digraphs available with the English alphabet. That's 24 times the variation possible with a monoalphabetic substitution cipher. Just like there are frequencies for individual letters, there are also frequencies for digraphs. Now what that means is that frequency analysis is still possible, but that you need a much larger sample to work with to be able to work out accurately those frequencies. The Playfair cipher was primarily used by the British military for tactical communication in the Second Boer War and World War I. It remained in use during World War II by coast watchers in Australia, New Zealand, and the Pacific Islands, where it played an important part in saving a future president's life. On August 2nd, 1943, an Australian coast watcher stationed on the Solomon Islands, Lieutenant Arthur Reginald Evans, noticed a fire on the water in the Blackett Straits. Now he didn't know what this was, but a short while later, at 9:30 a.m, he received the following coded message written in the Playfair cipher. The code word in use was Royal New Zealand Navy. Now, if you want to give this a go, pause now. The message he received told him that a PT boat had been lost in action in the Straits. Now, he put 2 and 2 together, and he connected the flame that he saw in the distance with the lost boat, and a rescue operation was launched. Hours later, by about 10 p.m, future President John F. Kennedy and his crew were rescued from the boats. Years later, shortly after becoming president, Kennedy hosted Evans for a special meeting at the White House. So that brings this episode of Codemaking and Codebreaking to an end. Thank you so much for joining us. This is the last episode in the series, and I appreciate you following along. If you missed any of the others, you can find links to them in the description below. Thank you.